So what we have here is Unit 2, which is linear equations in the energy market. And we're going to be discussing what solar installations look like today. So before starting this class, you should go just kind of look through these links to see kind of what information is out there. We'll use some of these links for the course of the class, and others are just there so that you have a little bit more information. So nationally, the average household uses approximately 11,000 kilowatt hours, annually. We're going to use the average annual usage to determine the daily average energy usage for a household. So I'm going to quickly teach you something that will be helpful for all of these conversions, and I'm going to walk you through it. It's just a trick for unit conversions, and they're called train tracks, and it will help you keep track of all of your units. So what we're saying is we have 11,000 kilowatt hours per year. And what we want to do is find out how many kilowatt hours per day that is. So normally we would multiply that by another fraction, which is that their 1 year contains 365 days. And that way we can cancel off the years and we can have kilowatt hours per day. And so we're going to divide that out. 11,000 divided by 365 is 30.13. And we're going to go ahead and keep track of our significant digits and say this is 30, and we're going to kind of pretend there's a decimal point there because we have two significant digits, not just one. Now, this is fine on this sort of a level, but when we start getting multiple units that we're trying to keep track of, it's a lot easier to do something called railroad tracks. And this is used a lot more in chemistry than it is used in math, because oftentimes in math we don't deal with units, we just deal with the numbers. But this class is a little bit differently. And so we set it up the exact same thing, 11,000 kilowatt hours per year. This is just a fraction. And then we know that we want to convert years to days. And we know that in order to cancel out the year that's on the bottom over here, we need to put a year on the top over here and days on the bottom. But we can't just multiply this arbitrarily by anything we want to. We need to multiply it by 1 so that it's the same. And luckily we know that 1 year contains 365 days. So we are equivalently making this fraction is equivalently 1. It just uses different units. And then the rule with railroad tracks is that you just multiply across the top, multiply across the bottom, and then divide. So we cancel our units, and this is 11,000 kilowatt hours divided by 365 days. If this doesn't make full sense right here, don't worry, we're going to repeat this a lot throughout this lesson. And so anyway, our answer to this lesson right here is 30 kilowatt hours per day. Okay. So moving on. Oh, and I forgot to fix my numbering here. It's all off by 1. So just just keep that in mind. Okay, we're going to use the turbine generator to find our state's average daily sunlight per year. So our average daily sunlight, our average daily sunlight per year is 3,000. Our average sunlight per year. Sorry, this terminology is really a little bit strange to me. So in a year in New Mexico, which is we're using, we get 3,400 hours of sunlight per year. So to find the average daily sunlight, we're going to want to set up our railroad tracks. We get 3,400 hours per year. And then we want, again, to figure out what this is in hours per day. So we want day on the bottom, and we want to cancel out year on the top. And we know there are 365 days in 1 year. And so this gives us, with our rounding significant figures, 9.3 hours per day on average. Now, next we're going to take our daily average consumption of energy, and we're going to divide that by our daily average sunlight in order to get the number of kilowatts our system needs to provide. So I'll explain that a little bit more here as we set up our equation. So our daily average consumption was 30 kilowatt hours per day, and we get 9.3 hours of sunlight per day. And so because we want to be able to cancel things out, we need to have our day, let me switch my color, our day on the top and our hour on the bottom. And we have 9.3 hours of sunlight per 1 day. And so we can start canceling some units. We can cancel out day and day, and it's a little less obvious, but we can cancel out hour and hour. And this is how we determine what how many kilowatts our system needs to provide. And so that is going to be when accounting for significant figures, which means, remember, we have 2 because this 30 right here has 2. This gives us 3.2 kilowatts that our system needs to provide. I'm going to confess I'm not an electrician. I'm not an electrical engineer. A lot of this terminology starts to be a little bit confusing to me, but what I do to get around it as a mathematician is I look at my units, and that tells me what I need to be doing in order to find out the answer, and I make sure that it makes sense. This isn't my strength as far as explaining exactly what's happening. I believe our kilowatt is the output that our system is putting out at any given moment, and kilowatt hours are the total output they put over the course of an hour. And that's just how energy is measured. But if you're really interested in this, you should go look up a lot more about how energy works, because that's a whole nother field that's very interesting. It's just a rabbit hole to go down into for this class. Okay, now we want to know what the number of watts our system needs, and we're going to set up these same train tracks. I know I'm telling you here just multiply by 1,000, but I want you to understand why. So 3.2 kilowatts. And then we're going to multiply we want our final unit to be in watts. So we need watts up top, and we need to cancel kilowatts on the bottom. And so we can just go look up this conversion, and 1,000 watts is in 1 kilowatt. So we just get 3,200 watts is what our system needs to produce. Okay. Now, this is another one that you just need to look up. You need to go look at the Energy Sage resource in order to find out how much your average state costs, your state average, how much your state's average cost per kilowatt or per watt for a solar installation is. This is basically the idea of how much each panel costs when you break it down by how much wattage each panel produces. So this is for New Mexico. Our average panels, or our average solar installation costs $3.21 per watt. So if we're going to take our average cost of $3.21 per watt and figure out how much our system would cost if it needs to produce everything, then we use our train tracks, $3.21 per watt, and we know that we need 3,200 watts in our system. We can cancel our watts, and we end up with a $10,000 system. This has 2 sig figs. It just rounded in a way that doesn't demonstrate that. Okay, so again, we're just making use of our railroad tracks to work out all of these conversions. Okay, so now this is the somewhat tricky question part. We're going to fill out this chart detailing how much money we've spent on this system. So right after it's installed, before we've started actually getting electricity out of it. This is what I'm looking for year 0, okay? The moment it is installed and we start getting electricity out of it, I want to know how much we've spent on the system. And at that point, we have spent $10,000 on the system. And now, after the system's been in use for 1 whole year, I want to know how much money has been spent providing electricity to my house for that entire year, for the whole first year of operation. That is still $10,000 because it's the cost we paid for the system, but once we installed the system, we're not incurring any costs. So after 5 years has gone by, the total amount I've spent for my electricity in those 5 years is the $10,000 on the system. Same with after 20 years, I've spent the $10,000 on the system. And after X years, I've spent $10,000 on the system. Now, this is not realistic in actuality. As the system grows older, you're going to need to perform some more maintenance over time, and do small repairs and things like that. And at some point, 100 years from now, we're saying X here, so X could be anything. X could be 1,000, X could be 100, X could be 30. The system's going to stop working. So this is incredibly unrealistic that you're not going to spend a little bit of incidental money here and there. However, it is realistic enough for the purposes of our algebra class. So now we're on to a full grid system. We're no longer looking at using solar panel. We're looking at using the electricity that comes from the wires, that comes from the central station. Because eventually what we're going to do is we're going to compare multiple systems to find out which one is the cheapest in the long run or the short run or anything like that. So the average cost of electricity in New Mexico in 2018 was $12.68 per kilowatt hour. What would the average annual cost of electricity for the average home be in dollars? So if you'll recall, way back at the beginning, I told y'all that the average home uses 11,000 kilowatt hours per year. And so now we know that electricity costs 12.68 cents per kilowatt hour. And we want to have this final outcome be in dollars. So we know that there are 100 cents per $1. Okay, so we're going to multiply across the top, and we're going to multiply across the bottom, which is just 100, and we end up with $1,400 when we account for significant figures. So $1,400 is the annual average cost of electricity in dollars in New Mexico, based on New Mexico's energy cost. So now we're going to fill out the same grid again, finding out how much we would spend on electricity cumulatively if we were on full grid. So in year 0, before we've started consuming any electricity, we have paid $0. In year 1, we have paid $1,400 because that's what we said a 1-year cost of electricity was. In year 5, we have paid $1,400 per year for 5 years. And that tells us that we have paid $7,000. In year 20, we have paid $1,400 per year for 20 years, and that tells us we have paid $28,000. And finally, in year X, we are paying $1,400 per year for X years. So we've discussed 2 options, the full solar model and the full grid model. These are kind of limiting because they assume that it's either an all or nothing sort of situation. There is a hybrid model where you can install the amount of solar that you have available in your budget right now. So we're going to walk through this pretending that you have $8,000 to spend. It could be a $2,000 installation. You could add a solar panel each year as you find the money to do that. Those are a lot more complex systems to look at, and we're looking at linear systems right now. So we're not going to discuss that at the moment. So we're discussing if you have an $8,000 to spend, we want to know how many watts your system can produce. And again, we're going to produce these railroad tracks. So we have $8,000 to spend, and we have a cost in New Mexico, and you'll use your state if you would like to. We have a cost in New Mexico of $3.21 per watt for a solar installation. And so we want to have our output be watts. We want to cancel out our dollars. So we're going to put our dollars on the bottom, $3.21 per watt. We are going to cancel our dollars out and take 8,000 and divide by 3.21. And with significant figures, that gives us 2,500 watts is how much our system will be able to produce each year. And now we want to know, or sorry, not each year, how many watts our system will produce total. We use kilowatt hours to talk about how many watts are produced in a certain amount of time. Okay, so how many kilowatts will our system produce? Again, we're going to set up our train tracks. 2,500 watts, and we want our output to be kilowatts. And we want to cancel our watts. So we have 1,000 watts per 1 kilowatt. We cancel our watts, and we divide by 1,000, and we get 2.5 kilowatts is what our system produces. And now, remember, we need to multiply by the hours of sunlight in order to find out how many kilowatt hours our system produces in a single day. So, set up our tracks again. 2.5 kilowatts. And then we have, we want our hours on the top and our days on the bottom. And we go find out what our average sunlight per day was. In New Mexico, that was wrong side. This is why we set up our tracks, because I started to say 9.3 hours per 1 day and realized that my units were wrong. Okay, so now this gives us, allowing for significant figures, 23 kilowatt hours per day. Okay. So now we want to find out how many kilowatt hours our system will produce in a year. So if it produces 23 kilowatt hours per day, and there are 365 days in a year, then our system produces 8,400 kilowatt hours per year. How many kilowatt hours will we need to get from the grid each year? Well, if you recall, the average household uses 11,000 kilowatt hours per year. And we're going to be producing 8,400 kilowatt hours in a year. So if we subtract these two, we'll know how much we'll be getting from the grid. And that is 2,600 kilowatt hours per year will be coming from the grid. So our yearly cost of electricity will be not the cost of our solar installation, just the amount we're spending on our grid electricity is, remember, we need to say that we have this 2,600 kilowatt hours per year. And in New Mexico, our electricity costs 12.68 cents per kilowatt hour. And we want our answer in dollars. So that's 100 cents per dollar. We cancel out our units to make sure everything works. So kilowatt hours and kilowatt hours, cents and cents. And what we're left is dollars per year. So if we multiply across the top and divide by the bottom, it works out with significant figures, digits, that we spend $330 on electricity per year. And you should be following along with your calculator. That's how you become comfortable with things like significant figures, and making sure you're doing all of this arithmetic right is by doing it alongside me and not just listening to me talk. So finally, we're going to fill out this chart of how much we're spending per year on electricity. So on this hybrid system. So in year 0, before we've started drawing any electricity from our solar panels or our grid, but after we've installed our solar panels, we have spent $8,000 on our electricity because we installed the solar panels. After the first year, we've spent $8,000 on electricity for our solar panels, plus $330 for our first year of electrical service. And so we get $8,330. Remember, when you are adding, let me say this, as I did in the thing, we're going to take liberties with the sig figs. We're just going to add. And the reason isn't because they're not important here. It's because we want a nice, clean, straight line on our graph. And in reality, this 8,000 is 4 sig figs. This 330 is 2 sig figs. We are really fine, but we're not even going to talk about them just because I would like to have our final graph be accurate or be straight, be linear, because this is a linear equations class. Okay, so for 5 years, what we've done is we have spent the initial $8,000, and I'm going to start leaving off my units simply because I don't have room for them, and they're all dollars. Plus, we have spent $330 each year for 5 years. So this gets us 8,000 plus 1,650. Which is $9,650. Once we've had the system installed for 20 years, we've spent $8,000 to get our solar installation up. Plus, we've spent $330 on grid electricity per year for 20 years. So that's our initial 8,000 plus 600, and we're seeing if I can multiply on the fly, $6,600, and we get $14,600 is what we've spent after 20 years of this installation. After X years, it's the same exact thing. We've spent $8,000 for our initial setup, plus $330 per year for X years. And that's perfect. We've filled out all of our charts. We're just going to combine them together on this one, which you don't need to see me copy a bunch of stuff over. And in our next class, we will get started on filling out our graph and answering our graphical questions.